proteins, and you show the with parallel counts. The resolved means for which you know this is pathogenic or this is benign, and VUS means for which you don't know. So with increased parallel counts for the resolved proteins, where you know this is pathogenic or this is or benign, the parallel counts becomes lower. But for VUS, it becomes slightly higher. Although it is not very strong correlation, but there is a trend. It was an encouraging example for me. So then I became a bit more courageous. So I tweaked my code to now do the analysis on, say, 13,000 proteins on the clean bar. So we could do that, and from there we also could see that when we extended it to thousands of proteins, then the trend is still there. For the VUS, you have, with the higher number of VUS, you have higher number of functional backups, but when you have lower number of paralogs, then most of those are resolved. So this gave me an idea that the hypothesis that I have given probably have some merits. It's not still proven, I'm still doing the work, but it gave me some confidence. I also checked using kind of the same skill that I have got in Lynch syndrome. It is one of the worst thing that we can inherit. It is a condition where some mutations in MLH1 or MSH2 or MSH6, if we have mutations in these genes, then we become more prone to develop certain cancers. And you can see the list of cancers on the right side. And it's a really big list. So colon cancer, then stomach cancer, pancreatic cancer, in female breast cancer, ovarian cancer, all these cancer risks become so high, almost 100%, when we have mutations in the genes. So this is a very severe case. So when we have Lynch syndrome in any person, then that means that their management should be completely different than other people. We all have risk of cancers. Everyone has risk of developing cancers. But for example, we have lifetime risk probably 5 to 10%, but for Lynch syndrome people, it will be 90%. That means completely opposite. So when we want to deal with these people, then we have to have more knowledge and we have to understand the biology a bit more better. So I wanted to see the genes that you have seen here, like MLH1, MSH2 or MSH6. I wanted to see, they have like hundreds of variants that you will find in these genes. I wanted to see if any of those variants, or that means any of this particular mutation, is more common in particular cancer. Now you can see from, although it's a bit difficult to read, but yes. So this is colorectal cancer, and you can see just from these dark spots that there are two variants here, two particular variants which are more common in colorectal cancer, and especially one variant is common in 5 different cancers. So that means that that particular variant, if we find that variant present in any person, then probably that person needs a bit more aggressive management compared to other people. So how I generated this image, again, I used the Copilot and I took its support and I asked that I want to do analysis. It gave me the code. It's not that I gave it the whole data and then it generated the image. It's not the case. It cannot do that. When we do that, then it gives lots of misleading results. But I got the code from Copilot and then used it in my R environment, that is R Studio. So for the first time using AI, with the help of AI, I could now use R Studio or the R programming, and I could generate some of this really useful information. So this is one of the examples, and then I want to go to another sector where I'm also working, which is drug combination in cancer therapy. When we have cancers have generally 6 hallmarks. That means they grow faster, they cannot be killed, they have lots of blood vessels, and they invade to distant organs, and they have enabling replicative immortality. That means their end of the chromosomes, the telomere, that they are not shortened anymore. So there are certain hallmarks that are present in cancer. So we are also doing research where we want to see whether in particular cancer, for example, if we go to colorectal cancer, then if you go in this direction, it's different cancer, but then if you go in this direction, these are the different hallmarks. So we can see, I'm not going to explain this too much, but we want to see how we can combine different hallmarks and then which hallmarks can be targeted to select particular drug for a particular cancer. So if a particular, for example, if lung cancer, for example, for lung cancer, this sustained proliferative signaling, it has got very deep color. That means this is very strong in this particular cancer, but probably these are not very important for us. So when we combine drugs, then we probably focus on this particular hallmark and this hallmark, or probably these hallmarks. So using these multiple targets, we have higher chance of treating cancers than before. So this is another example where I'm also using AI to bring information. So really find the drug targets, and then how what we know so far about the particular drugs, or the mechanism of actions, and which hallmarks can be targeted using that particular drug, and how we can then combine those drugs. So this is possible now because of the application of AI in my particular research. And I think this is kind of the last use case for me. So here I wanted to